Thank you very much. So I'm going to tell you a little bit about recent investigations we've been making, comparing realistic hydro simulations with observations, asking the basic question, how well do we recover what we put in? So it seems like everyone here has an advanced degree in filmmaking. So here's our beautiful movie. We're sweeping around one of these massive Vela galaxies. And what we do is we take the star particles here in the gas grid, and we forward model and predict these velocity maps as we would see them from telescopes. So as I said, this is one of the disks from the Vela simulation. But let me remind you about Susan's talk yesterday. What are we learning from our observations? So from redshift 2.5 to now, we find that star-forming galaxies decline in sigma g. The sigma g term is, you could just think of it as just disordered motions. Just random motions resolves random motions. We find that it drops by about a factor of 3 from redshift 2.5 to now, and it doesn't depend on mass. So that's very interesting. Ordered motions, rotation velocity, increase with time or remain constant, as Susan showed. When you properly connect galaxies in time with abundance matching, these relations become more steep because they're growing in mass with time. Okay? And then if you take those two things together and examine the fraction of galaxies which meet this criteria, V rho over sigma g greater than 1, that means that they are rotation dominated, you find that galaxies form disks with time and massive galaxies form disks first. And then when you plot everyone else in the literature, this is a big industry, you find that everyone's in agreement that galaxies or disks form with time, and it's really a lot of mass describes any discrepancy between surveys. But this fraction is a very important bellwether. We need to really understand if we're pinning it down. Why is it an important bellwether? If it's low, then that implies that mass assembly at redshift 2 is violent. If it's high, that means the mass assembly is calm and hospitable to disk formation. The reason is these are gas-based measurements, so you should expect gas to cool, form a rotating disk on a crossing time, or a couple of crossing times. Okay, so how well do we understand these measurements of disk fractions? Well, there are two problems. One is that we're all using one tracer. It's an emission line, so it's the warm ionized gas, and it's not clear how well that traces the remaining baryons in the galaxy. Two is that there's seeing. The PSF, the resolution that you get from the ground, at best is 0.5 to 0.8 arc seconds, which is about 5 kiloparsecs at redshift 2. So at most, you get only a few resolution elements. So when you measure a velocity gradient in a galaxy at redshift 2, it's unclear if it's truly a rotation velocity. So I'm going to be using the Vela simulations. As I said, we're going to forward model these and predict kinematic maps. So these have made their rounds during this conference, so I won't talk about them that much. There are 34 of them. They span the stellar mass range comparable with the surveys in the literature. All of the architects are in the room, so if you have any questions, I'd say ask the experts. So we're going to look for intrinsic disks in the simulation using this JZ over JCirc parameter. If this is 1, it means all of the particle is on a circular orbit that's co-rotational with the rest of the galaxy. If it's 0, that means that it's perpendicular. So just for this parameter, look for 1. That means that there's a disk. Look for 1. Okay, so the first question, how well are we actually tracing the remainder of the baryons with the old stars or the cold gas? So here's the answer. The young stars, which is a proxy for the emission lines here, trace the cold gas pretty well at most redshifts. Again, this is a side note, but Vela follows disk settling. Disks form with time. You see that? The massive galaxies form disks first. I said look out for 1. All these galaxies are moving towards 1. But one thing to note here is the old stars are always a lot more dispersion dominated than the young stellar population. So we're always going to be biased toward the most rotationally supported component when we're measuring the emission line. And here's some nice work showing that the cold gas and the young stars tend to trace each other. Young stars being a proxy for H alpha from the FIBS survey. So we could also, as I was saying, we mock observe these galaxies. So we, through sunrise, we replace all the young stars with a mappings 3 model, put 19 cameras around each galaxy, and you generate idealized maps. That's what this top row is. And from there, you do a post processing. You surface brightness dim them, you add a lot of noise, and you end up with these nice maps as you would see them from the ground. So we have a machine to generate mock observations for really any telescope or any observing condition. So here's just what these maps look like. Here are the HST candles-like images, and then here are kinematic maps for a KMOS survey. And I mean, look how much, there's rich detail in here, right? So that's one of the points of this talk. Okay, so this is showing the companions around the Vela central galaxies. So let me walk you through this. These are all 34 simulations. Each point here is a single redshift for a single galaxy, and it's color-coded by whether or not there's a major or minor companion present. And what I'm going to talk about are these galaxies down here. Remember the disk lie here, JZ over J circ near 1. These galaxies are not rotating, but they have a companion, and there are a lot of them, especially out at redshift 3. You see that it's very common for these central galaxies to have a companion. So here's an example of 2 galaxies. One has an intrinsic disk. These are the stars. This is JZ over J circ versus radial distance. You see this one has a nice disk. It's one of the more massive ones. This one does not have a disk. There's 2 galaxies in here. This one is not rotating. This one is a companion. But when you look at the kinematic maps, you see the rotation fields look almost identical. You get a nice smooth velocity gradient. You have a peak in the sigma map, maybe not here, at the highest where the gradient is the largest. One thing you could say is, okay, but there are two blobs here. That's fine. I'll just remove those from my survey. Here's one where it's not as easy. This one also does not have an intrinsic disk. It just had a merger. The disk or the companion is within 10 kiloparsecs, and again, the velocity field looks like a rotating disk. So rotating disk, not rotating disk. It's very difficult to tell them apart. Okay, so now if we plot the okay, so let me start on the right panel first. This is the fraction of sightlines. So I said we have 19 camera angles around each galaxy. These are isolated galaxies that have disks in gray. You see that the disk criteria that we use are actually really good when the galaxy is isolated. There's a confidence level of about 90% that you would identify it as a disk. The problem is when you get a companion. So this is versus the distance between the companion, especially when the companion is within about 10 kpc. You end up with all of these false positives here. This is 60% in red are galaxies without disks. 60% of the sightlines you would identify them as a disk because the orbital motion is getting smeared and you interpret it as rotational motion. And then you also notice that the scatter down here has increased, and that's because now you have disks which have companions that are masquerading as non-disks. So it goes both ways. You have non-disks that are masquerading as disks. You have disks that don't look like this. I'll show you the second case in a second, but I just want to say that the implications for the observations are that these fractions that we measure, which I argued are one of the most important bellwethers we have for whether mass assembly was violent at high redshift, are okay if there are not very many galaxies with close pairs within 15 kpc. they're overestimated if the close pair fraction is high. So this is something that is important to measure. I come from Hopkins, which is right across the street from Space Telescope. So I'm a big fan of James Webb. I get a lot of James Webb influence. So I want to show you. What the situation will be like once we have Webb. So here's a simulated image. It's a merger. Here's a galaxy. Here's a galaxy. Galaxy 1, Galaxy 2. This is one of the cases where the merger is actually drawing the kinematic map. The orbital motion is drawing the kinematic major axis. You see, you can actually make out the disk motion here. Here's a Galaxy 3. This is what it's going to look like with Webb. There's a lot of rich detail in here. You end up with this major axis separates. You end up with this major axis here of the disk, this major axis here of the orbit. You end up with this minor axis, or there are at least 3 kinematic axes here. So we have to start thinking about these as we do the images, where you don't just apply one number. Everything I said today applies more so with the slit data. I'm not here throwing mud at the IFUs. They're just the best 3D picture that we have of galaxies at this redshift. So I'll just leave out my summary. Thank you.
I wonder whether you can separate mergers and rotation because of the amplitude of the velocity.
Yeah, so you think that the escape velocity is about square root of 2 times what the circular velocity will be. So it's almost there. It would be a tough measurement. Yeah, that's a good point though. There are also inclination effects, so the error bars become fairly high. Yeah, that's satisfying. Yeah.
You can't combine the images with kinematics. You haven't done so. Principally, you use it as a double. Combine that as a total experiment, not just use it.
That's right. Yeah.
So, pretty sure that which ones are reliable measures.
Yeah, I think so too. I think incorporating right now. Yeah, I fully agree. I won't. Yeah. Mm-hmm. Yeah, but that hasn't been done yet. But timescales are one of. I mean, where's Kamiswara? Yeah, that's a big factor when you're converting close pair fractions to actual merger rates. It hasn't been done yet though. That's a good point. I think Hannah has a question.
How many others there out there that can maybe hold this in a systematic error, so when we try to quantify any of those distractions and so on.
I agree. Yeah.
Okay.
Okay.